Hi, I'm Eric Lerner with LPPFusion, and welcome to the first episode of our new series, JWST and the Big Bang Never Happened debate. Now, the only reason we're having this debate is that a few weeks ago, this article appeared in the Institute of Arts and Ideas, and it started to get a lot of traction and circulated, and that's how we started to get replies. So thanks to Darcy Boonsall at the Institute and to Dr. Jayant Narlikar for introducing us. So what has happened is that people like Brian Keating and Dr. Becky and Anton and a lot of others have actually started replying. And that's great because that's much better than ignoring the debate, which is what all of them and others have been doing for the last several decades. Unfortunately, they haven't started replying to my actual scientific points yet, but hopefully that'll come. So in this video, we're actually going to concentrate on the most important single scientific point that I made in the article. And hopefully they'll reply to that. So let's get started. I think we're going to start with some things that we all agree on. So the first thing, we're going to be talking about redshifts. So let's start with the redshift. The redshift is the process by which the wavelength of light shifts to the red. And the red end of the spectrum means the wavelength gets larger with increasing distance. Galaxies that are further away from us, their spectra are shifted to the red. And we know that because we have these patterns of lines, dark lines and bright lines, and we see that pattern shift to the red end of the spectrum. Second thing we can agree on is in the Big Bang hypothesis, which involves the universe expanding, if the universe is expanding, distant galaxies were closer when they emitted the light, so they should look bigger on the sky. So in this diagram, the galaxy that's labeled S was closer to us when it emitted the light. So we see the angular diameter, theta 2, that's the angle we see it on the sky, its apparent diameter, as it was when it emitted the light. But now it's much further away. But we don't see it as it is now, we see it as it was when it was closer. The ratio of those two distances is the redshift. That's the amount that the universe has expanded over that time. And that's symbolized by the letter Z. And that's what is measured by the redshift. So if the universe is expanding, more distant galaxies beyond a Z of about 1.6 look larger, not smaller, with increasing distance. So this is a graph that shows the angular radius of a galaxy the size of our Milky Way galaxy. And angular size in arc seconds is plotted against redshift Z. Now, an arc second is a pretty small measure of apparent size. So it's the size a baseball would look if you held it at a distance of about 8 kilometers or 5 miles. It's pretty tiny. But our telescopes can see these tiny angular diameters quite easily. So the main point is, contrary to what happens here on Earth, as you get further away, the galaxy looks bigger, if the Big Bang happened. If there was no Big Bang, if the universe is not expanding, then objects look smaller in proportion to distance, just like they do on Earth. So the angular diameter equals radius over distance. R is the linear radius of the galaxy. The radius it intrinsically has so many light years, and D is the distance. Since we observe at low Z that the redshift, Z, is proportional to distance, Z equals HD over C, where H is the Hubble constant and C is the speed of light. If this is true everywhere, and everywhere theta equals HR over ZC. So theta, the angular diameter, if the universe is not expanding, is inversely proportional to Z, the redshift. And conversely, if we observe a galaxy at redshift Z and it is observed to have an angular diameter of theta, and we calculate its radius R to be theta Z C over H. Now, from this, I and my colleague Ricardo Scarpa, before JWST, predicted in a paper that we had to publish ourselves online, but was published online before JWST, that for galaxies of a given mass, galaxies of a given luminosity, the angular diameter would decrease as 1 over Z. And we were predicting that the linear galaxy size for a given luminosity or mass would be the same at high Z as low Z. So what we're trying to execute is the Tolman test, or the angular size test. It's also sometimes called surface brightness test. The angular size of galaxies of the same luminosity at different Z is a test of the expansion of the universe. And this test was proposed 90 years ago by Tolman back in 1931. So if we put these two models, these two hypotheses on the same graph, again, plotting the angular radius on the sky of a galaxy the same size as the Milky Way, we get two very different predictions. With the Big Bang expansion, the angular size goes way up with high Z. With the no Big Bang, no expansion, it gets smaller and smaller. If we flip this formula upside down and we say, if we observe a galaxy with a given angular size, and how do we calculate its linear size? And what we say is that the linear intrinsic size is calculated to be different for the expanding and non-expanding universe hypotheses. So this is a graph that again puts these two hypotheses together. Now we're talking about the linear radius of a galaxy observed to be 1 arc second in radius on the sky. So we observe the 1 arc second, that's the observed quantity, and we calculate the linear radius. No Big Bang, no expansion. At high redshift, these must be large galaxies, kiloparsecs. But with the Big Bang, these galaxies are very, very tiny in linear dimension. So that's the angular size test, and we're going to apply that to the actual observations. Now, before we get to the actual observations, let me just say, why does this matter? Does this really matter whether the universe is expanding or not to us here on Earth? And I think it does, because unless we get rid of the incorrect Big Bang expansion hypothesis, we can't understand how the universe actually evolved, how it produced the galaxies, how it produced the stars like our sun. If we do correctly understand these processes, which involve the interaction of electromagnetic forces and gravitation, then we can implement these processes and imitate these processes here on Earth in the laboratory. And that gives us the ability to generate fusion energy. And fusion energy is the energy that we badly need right now to replace fossil fuels. So this is why this matters, and we'll get into this more in other videos. So let's look at the data, the actual observations. First, let's look at the observations that were available before JWST, the Hubble telescope observations. Now, we're measuring things in parsecs, and 1 parsec equals 3 light years. So in this chart, we are measuring the mean radius of samples of galaxies. So each of these red and blue and black points represents the mean radius of a sample from dozens of galaxies to hundreds or even thousands of galaxies. And this is plotted, the mean radius of these samples against redshift. And I published these results in the monthly notice of the Royal Astronomical Society, one of the leading journals, back in 2018. So you know it went through a pretty tough peer review process. And as you can see, there is an excellent agreement to the hypothesis that the radius is the same for galaxies of the same luminosity at all distances up to a redshift of 6. So when Ricardo and I made the prediction that this was going to be true for JWST at higher redshifts, we weren't really going out on a limb. We knew that this prediction had been already confirmed with Hubble. So what happened with the JWST, where we've only got, of course, the first month's data? Well, what we're plotting here is individual galaxies. And what we're plotting is the blue dots are individual galaxies with HST galaxies on the left and JWST galaxies on the right. These are extremely bright galaxies. And the blue dots are their radius as calculated if the universe is not expanding. The orange dots are calculated if the universe is expanding. So what you can see is with the blue dots, the prediction that galaxies at high redshift are approximately the same size, they're pretty accurately the same size as galaxies at lower redshift, is still very good. Basically, our galaxy is around here at 15,000 parsecs in radius, and you can see that all these galaxies are within a factor of 2, either twice as big, half as big, or in between. So that prediction is actually very well fulfilled. But it was very surprising to people who, as most cosmologists, believe that the universe is expanding, because what they saw, what they calculated, was galaxies that were already 10 times smaller than present-day galaxies with HST. But with JWST, they're as much as 40, 50, 60, 70 times smaller than the galaxies that exist today. To take an extreme example, galaxy that is called GHZ2, is this what I would call a Mighty Mouse galaxy? Extremely small, but extremely dense. Well, if we take the same galaxy, the same data, and we calculate it on the no Big Bang assumption, it looks pretty typical for a large galaxy. It has a radius of 6,000 parsecs, a little smaller than the Milky Way. A luminosity, pretty similar to the Milky Way galaxy, which is about 100 billion suns. The surface brightness, the ratio of brightness to area, is about half the brightest galaxies we see around us. And the same with the volume brightness, the brightness per unit volume per unit of space. Pretty typical. But if we use the Big Bang assumptions, we get something that doesn't look anything like what we see in the galaxies of the present day universe. The radius is only 90 parsecs. The luminosity is about the same. And in another video, we'll get into why that's so. But the surface brightness is 600 times the brightest galaxies we see around us. And the volume brightness is 14,000 times. So we don't see anything like these Mighty Mouse galaxies around us today. So that leads to the first set of questions for Brian and all the critics. First of all, science is about accurately predicting observations before they occur. Which hypothesis accurately predicted the size of the galaxies observed by JWST? Those who worked from the expanding Big Bang hypothesis were surprised. Doesn't that mean their predictions were wrong? And conversely, isn't it true our predictions were right? Second, how could the surprisingly teeny tiny but bright and massive galaxies that the expanding universe formula calculates from the JWST images grow into the 50 times larger galaxies we see today? And if they didn't grow, where did they go? I mean, we couldn't overlook such teeny tiny super bright galaxies. They're the brightest galaxies in the sky. Third, we know that cosmologists have been saying for years that these galaxies grew by colliding with each other. All right, we'll get into that in the next slide. Is there any other process than collisions or mergers that could possibly work to make these galaxies grow? Well, I think the answer is no, but we'll see what Brian and company says. If the answer is that collisions were the only way they could grow, we sort of have this scenario. Imagine a toy truck about 6 inches long, but nonetheless having the mass of a big SUV. And the collision idea is that these little trucks are colliding with each other and sort of smearing each other out until they grow up to great big SUVs. Yeah, there are sort of plausibility problems with that argument, but certainly you would expect some dents in these cars, right? Well, that's actually what cosmologists did expect about the galaxies, which gets us to why the panic at the disks. Now, people have said, oh, I missed the pun, panic at the disco. Well, why was it panic? Why not joy at the disco, excitement at the disco? What was wrong with these galaxies? Well, the galaxies were too smooth and the spirals were too old. What these images, and these are images that are blown up from the famous first JWST image that everybody's seen, they show very smooth, very well-structured spiral galaxies at all redshifts. Most galaxies look like this. Well, what does that mean? What that means, and what the authors concluded, is that they couldn't have undergone many dozens of collisions to grow up from tiny galaxies to great big ones. What the authors wrote was, we in fact find that at the highest redshifts probed by HST and now observed by JWST, there were 10 times more disk galaxies than we had thought. It's roughly 50% of all galaxies. This implies disk galaxies have existed in large numbers for quite a significant length of time, billions and billions of years. this would challenge our ideas about mergers being a very common process. Well, this is sort of astronomer modest speak for this would totally blow away the theory that collisions made these galaxies grow up. It totally obliterates them. And that's why the authors were joking that it could cause panic, not among themselves or observers, but among the theoreticians. So that leads to the second set of questions for Brian and the gang. Since the observations of disks or spiral galaxies at all redshifts precludes the frequent mergers or collisions that might conceivably grow the tiny galaxies into big ones, how could this growth happen otherwise? My answer, it couldn't. We'll see what Brian and company answer. If there is no way that the tiny galaxies can grow, and since we see no such ultra-dense galaxies today, how could have they been tiny in the first place? My answer is they couldn't. If the galaxies were in fact never tiny, then doesn't the expansion hypothesis flunk the Tolman test? How could full-size galaxies look so tiny on the sky unless there were no expansion and thus no Big Bang? So in summary, the Big Bang expansion hypothesis predicts galaxies look bigger on the sky at high redshifts. No expansion hypothesis predicts they look smaller. JWST sees small on the sky, bright, massive galaxies, as predicted by the no Big Bang hypothesis, but very surprising to Big Bangers. If there were expansion, these galaxies were 30 to 50 times smaller in real size than present-day galaxies and had to grow enormously by collisions. The prevalence of smooth disk galaxies shows that collisions were too rare to generate this growth. Since the growth could not have occurred, the galaxies could not have been tiny. So the expansion theory prediction is contradicted. The expansion is not occurring, and there was no dense period of cosmic evolution, no Big Bang. The redshift distance relationship is not caused by expansion, but by something else that occurs to the light as it travels. So that's the story for today. In the next video, we'll get into some of the non-technical arguments that our critics have used to say why you shouldn't pay attention to me in particular. And we'll continue also in future videos with the technical discussion. In the meantime, of course, our research needs funding, and in the description, you'll find out how you can support our research, because we don't have any other form of support except the general public. And in the process, you'll also support our research into development of fusion energy.